All right, let's talk about the mean value theorem. This is section 5.2. The mean value theorem is not counterintuitive unless you go straight to a graphical explanation of it. Let's talk about just a real-world application of it. All right, so in the Ohio Turnpike or any turnpike, when you enter, usually you get a timestamp ticket. All right, so let's just think about the Ohio Turnpike. The speed limit for trucks is 60 miles per hour. So suppose it takes a truck driver 2 hours to drive between two toll booths that are 130 miles apart. Okay, I want you to maybe pause the video here and think about these questions. What's his average speed? Did he break the speed limit at some point? How do you know? Do you know when he broke it, if he did? How about the amount of time he was breaking it? Okay, so pause it, think about it for a second. Okay, hopefully you did that. All right, so hopefully you concluded that actually he definitely broke the speed limit at some point, because 130 divided by 2 gives you an average speed of 65 miles per hour. That's the truck driver's average speed. We don't know for how long he was breaking the speed limit. We don't know, for how long he was going 65. We don't know when the truck driver went 65 miles per hour, but we do know that he must have gone over 60 at some point. In other words, he was speeding at some point, because there's no way that you can average 65 without at some point going over 60. Okay? So that means that at some point in the interval from hour 0 to hour 2, he was going 65 miles per hour. He was going the average. So if we look at that in terms of mathematics, so let's suppose we have some function f of x. We need two conditions to meet the mean value theorem. First, the function has to be continuous at every point on a closed interval. And so that's including a and b. You can pick some a value and some b value. Right? And it has to be differentiable at every point on the open interval from a to b. Then, if those two things are met, then there is at least one point c on that interval in which the derivative is equal to the average rate of change. In other words, the instantaneous rate of change is equal to the average rate of change. Go back to the turnpike for a second. So what that says is that at some point, the instantaneous rate of change, how fast the truck was going, has to be equal to the average speed, which is 65. So to sketch that out real quick, these 2 points would be, this would be a f of a here and b f of b here. You find the average rate of change between them. That's the slope formula, slope of the secant line. At some point c, there has to be some point c in here that has a tangent line that is the same slope as the secant line. So I don't know, maybe it's like right here. I don't know, hard to tell, but it's somewhere in there. Okay, so we have a tangent line with the same slope as the secant line. And that point, we're going to call that point C. Okay, so, where this slope here is m equals f prime of C. All right, let's see if x squared satisfies the hypotheses for the mean value theorem, and then we'll find the C value. Okay, we're going to look on the interval from 0 to 2. And let's see if it satisfies the hypotheses. First of all, the first hypothesis is yes, it's continuous. All right. The second hypothesis, yes, it is differentiable on the interval from 0 to 2. Real quick, how could you prove that? If you found the derivative, you'd find that it was 2x. 2x has a domain of all real numbers. Because the derivative always exists, it must also exist on the interval from 0 to 2. Okay, so we're good there. It does satisfy the hypotheses of the mean value theorem. Next part, we need to find that solution C. So what we'll do is find the average rate of change. Right? We're essentially going to find both parts of this. We'll find the average rate of change, and then we'll solve for the C value. So let's start with the ARC here, ARC, that's going to be equal to f of b minus f of a. So that's going to be f of 2 minus f of 0 divided by 2 minus 0. That's going to be equal to 4 minus 0 divided by 2 minus 0. and that's going to be equal to 2. Okay, so we want to find when is the derivative, when is the instantaneous, when is the slope of the tangent line equal to 2? So we're going to set y prime equal to 2. In other words, we'll set this up. 2x equals 2, and we'll solve. We get that this happens when x equals 1. Okay, so that's the c value. That's the point at which the tangent line has the same slope as the secant line. Let's look at the picture over here. So if we're looking from 0 to 2, okay, and we draw in the secant line at the point 1, comma 1, that's where the slope of the tangent line is the same. Okay, so that's the c value right there, is that 1. All right, let's see if we can show this one satisfies the hypotheses of the mean value theorem. We're looking from -1 to 1. All right, I'm not sure how many times this is, if this has been explained to you or not, but square root of x squared is the same as absolute value. That's actually the definition of absolute value. So this could be rewritten as f of x equals the absolute value, try again, absolute value of x plus 1. Okay. This function is the absolute value of x just moved up 1 unit. In other words, if you think about what the sketch of that looks like, move it up 1, it looks like this. It's a v. Okay. So does it satisfy the hypotheses? Well, it's continuous from -1 to 1, if we put -1 and 1 on here. It's continuous for sure. Is it differentiable on the interval? No, it's not. We have a corner right here. So this one is no. It does not satisfy the hypotheses for the mean value theorem. Okay. All right, implications of the mean value theorem. So like I said at the beginning of this chapter, a lot of what we're doing now is formalizing things that we've already sort of relied on earlier on in the trimester. So the implications here, let's see. So f, again, is continuous and differentiable. So the same thing as the mean value theorem for the hypotheses. Then if f prime is positive at each point in a, b, then we say f increases from a to b. All right, and if f prime is negative, then f is the original function is decreasing on a to b. Again, this is something that we've talked about and used multiple times, but it actually all relies on the mean value theorem. Excuse me, as far as mathematical justification. So okay, so this one, we're going to figure out when the function is increasing, decreasing. We're just going to do number 4 because these problems can be sort of long, and number 4 is a little more complex. I already started the derivative here. So when you take the derivative of -x over x squared plus 4, you get this. And when we simplify, we're going to get -x squared minus 4 minus 2x squared. Oh, sorry, this would be -x here, right here. Okay, so it's going to be plus. So when everything shakes out, it'll be x squared minus 4 divided by x squared plus 4 squared. All right, so we want to find the critical points. We want to figure out when this function is 0, and we want to figure out when the function is when the function doesn't exist. So if we want to know when a fraction is 0, we just set the top equal to 0. So when is x squared minus 4 equal to 0? You solve that, you get x equals plus or minus 2. Okay. Then we want to know when is the denominator 0. Well, that's going to be whenever x squared plus 4 squared equals 0. And if you do the math on that, you'll find that it never happens. Okay, so let's do a sign chart. In other words, that is all to say that our only critical points are -2 and 2. Okay, so we'll check a point to the left of -2, so maybe you plug in -3. Note that the denominator is always positive. When I plug in -3 up here, I get 9 minus 4, which is +5. Positive over positive is positive. If I plug in 0, I get a negative number on top, positive on the bottom, it's negative. If I plug in 3, I get positive over positive, it's positive. So we can say that the intervals of increasing then are from -infinity to -2 and from 2 to infinity. Now, the AP test is sort of picky. You can't, if it says to justify your answer, you can't say that your sign chart is the justification. You actually have to write this out, what I'm about to write out. So you have to say, since f prime is greater than 0 from negative infinity to negative 2, and from 2 to infinity, f of x is increasing on those intervals. Okay, so that's only if they say to justify your answer. You can't just write, look at the sign chart. It's awesome. Okay, so then you could also say it's decreasing on negative 2 to 2. Again, you're going to use parentheses when you write those intervals down. Okay, so that's, again, if it just asks you to justify your answer on the AP test, like on a free response question, that's what you're doing. All right, this one, we want to find the function whose derivative is y equals sine that passes through the point 0, 2. We've already had problems similar to this, but we haven't dealt with this thing, which is where we add a point to it. Okay, so here, if we want to find the function whose derivative is this, we just need to antiderive. So, in other words, that's all to say that if f prime of x is equal to sine of x, then f of x has to be equal to negative cosine of x plus c. We're anti-deriving. We have got the derivative. We want to get back to the original function. So now we know that this function here goes through the point 0, 2. So we can actually figure out what the c value is. I know what x is. I know what y is. I can figure out c. So I'm going to go 2 equals negative cosine of 0 plus c. Cosine of 0 is 1. So I have negative 1 equals, so negative 1 plus c equals 2. So c has to equal 3. Okay, so we can write that our final function then is f of x equals negative cosine of x plus 3. Let's do another one of those. Find the function whose derivative is f of x equals 1 over x cubed at point P is 1, 0. You should try this one on your own. Pause the video, try it, and see if you get it right. This is saying that essentially f prime of x, I probably shouldn't use f here. Let's just write this, I guess, that y prime is equal to x to the negative 3. So if you want to know what y is, the original function, you're going to add 1 to the power and divide by it. So it's x to the negative 2 divided by negative 2 plus c. Now I know that the point 1, 0 goes through this function, so I can use that to figure out what c is. So I'll plug in 0 for y. I'll plug in 1 for x, so that's 1 divided by negative 2 plus c. And so c ends up being a positive 1/2. Because of that, I can write that my final function is y equals excuse me, x to the negative 2 over 2 plus 1/2. All right, last question. Find velocity and position functions for an object propelled downward at a rate of 1 meter per second, starting from a height of 10 meters. The acceleration due to gravity is 9.8 meters per second. So all we really know right here, if we're trying to figure out, some context. We're trying to figure out the velocity and the position function. All we know really is the acceleration function. We know that a of t is equal to 9.8. Negative 9.8. It's in the downward direction. Okay? So what that means is I can work backwards, or because I know calculus, I can work backwards to velocity. So if I anti-derive negative 9.8, I get negative 9.8 times t plus c. Okay? Now, the question is, what is that c value? Because that's going to be really helpful. Well, if I look, I know that the initial velocity is 1 meter per second. Over here, it's 1 meter per second. So if I know that v of 0 is 1, so in other words, this is saying that v of 0 is equal to 1, then I can write this. 1 has to equal, well, it has to be c, but I mean, I guess you could write it out. Negative 9.8 t, negative 9.8 times 0 plus c. What you end up with is c equals 1. In other words, your velocity function is equal to negative 9.8 t plus 1. Okay, again, that's because you're plugging in the point 0, 1 into your velocity function solving for c. We can get back to position too. So if I want position from velocity, I anti-derive, add 1 to the power, divide by it. So I'm going to end up with negative 4.9 t squared plus t plus c. Now I know what the initial height is too. The initial height is 10 meters. So in other words, when t is 0, the height or position is 10. So 0, 0 has to be 10. So c has to be 10. So my position function, s of t, has to equal 4.9 times x squared plus x plus 10. Okay, so given the initial velocity and position, we can work backwards from acceleration to get velocity and position functions. And that's it for section 2.